Okay, so we're back for the final segment of this last lecture on antivirus techniques or anti-malware techniques. So we're going to continue with modern malware scanners and how they work. So we'd already talked about algorithmic scanning. Now we have the idea of code emulation. So this is essentially using a really simplistic virtual machine to actually execute the malware in. What we can do here is simulate the CPU and the memory management to basically just run the instructions and see what they're doing, as well as mimicking any modifications that might be made to memory. This isn't like a full-blown virtual machine that we're used to, right? It's not interfacing too closely with hardware or anything like that. It's really just trying to simulate the instructions in memory that the executable is going to be accessing and manipulating. The goal here is so that we can maybe execute something to the point where it's decrypted a malware body, we can stop the emulation, and then we have a copy of the decrypted code. Or maybe as we're emulating something, we can have certain triggers in place that look for sequences of operations that we know to be malicious. At that point, the emulator will flag something as being a malware sample. The big problem here is that when we're emulating something, when do you stop running the emulator? If you're running a sample that you're not sure is malicious, how long do you run it for? Do you let it go for, an hour, 10 minutes, 30 seconds? Do you let it go for a month? What's really going to, indicate when the malware is either done or the file's malware or not? Turns out we can't really know this, right? The reason, we use the term like when do we halt it is because it's a reference to Alan Turing's halting problem, which basically says we can't really know, for example, if a program will ever exit a particular loop or not. So we have to come up with some basic flags, some heuristics to look for so that we know at least when we can stop the emulator. So some things that we can do, maybe we only have the emulator running as long as there's, active instructions executing. So in this instance, active instructions would be, things that are operating on the data segment in memory. So that means the program's actually actively making changes and doing things. So we want to continue monitoring it. An example is that, two adjacent memory modifications. So, I modify something at memory address 123, and then I make the same operation at memory address 124, and then the same at memory address 125. So we can see that in the code we're modifying adjacent values in memory. This could indicate that there's some kind of decryption going on. Maybe we're reading it, we're decrypting that byte and putting it back into memory. The problem is that we can't really know that. It could just as easily be a for loop that's iterating over a string and converting it to uppercase. We don't really know, but at least it's a type of instruction that maybe we want our program to sort of look for. Another way of terminating the emulator is to set breakpoints within the code, maybe at interesting sections. So we can do a quick pre-scan of the code and throw in breakpoints, in certain error handling routines or at known functions like the exit functions and stuff like that, and just run until we hit a breakpoint. It's kind of it's not an exact science, right, when to insert these breakpoints. We also, with virtualizing, we get the ability to monitor and observe a program. So with that, we can kind of build up this notion of heuristic detection. Heuristics would be using rules to observe the behavior of a piece of software. And if it violates one of those rules or a sequence of those rules, we could determine that it's malicious, right? So we can either specify a specific behavior, or we can specify maybe flags, which would be fixed values within inside of a file. Combinations of behaviors and flags that we see could indicate a heuristic for us. There's also the notion that we can assign weights to heuristics. So for example, down here is a list of things that you might look for, like maybe code execution starts in an abnormal section. So maybe not at the beginning of the text section, but maybe that rule alone isn't sufficient. So some approaches that have been used are like assigning a weight to that rule, right? And every time the sample triggers a certain flag or a behavior, you sort of add that weight to this growing suspicion factor of that software. And when it passes a certain threshold, maybe we've decided it's violated enough of our rules that we're going to flag it as malware. Right? So there's a number of different ways to do this. So some other things that you could look for, maybe the virtual size or the size of the code segment or something like that in the actual section itself doesn't match what's listed in the header. right? Maybe that indicates that a lazy piece of malware wrote its code into the text section but didn't update the header fields, right? So that kind of inconsistency might be a heuristic. Maybe suspicious code redirection or section names, right? You've got a section with a strange non-standard name, like it's not code, it's not RO data, it's not any of the other ones that we're used to seeing. So it might be the start of a heuristic. Maybe imports from third-party libraries by what we call ordinal position. So in a program, you can import a function from another library, like the string library, for example. You can import a function not by name, but by a numeric offset into that library where the first instruction in that function would be. You can do this if you want to conceal the function that you're importing because you don't want its plain text string name to show up if someone runs strings on your sample, right? So that's what importing by ordinal is. However, if our code sees an import by ordinal, obviously that's suspicious because no developer would ever write code that way. A similar heuristic might be, if we're executing a function by calling a register, because typically we call a function by its function name. But if we load in a memory address into a register and we call the register, that might indicate something suspicious. It could also just be, a dynamic function or something like that. So there are legit reasons why that might happen. But again, we can add up a number of these heuristics to eventually determine if something's malicious or not. The cool part about heuristics is that once we can start defining rules and metrics and things like that, we can teach machines to do that analysis for us. So there have been examples where people have trained up neural networks to spot and identify really complicated metamorphic and polymorphic malware samples. So it does work. The challenge with some of that, there's a few challenges. One of them is that malware authors can adjust the behavior of their malware or their newer samples because they know what the heuristics are that the AV vendors or some of the networks are using to identify the malware, right? So if I know that you're always looking for weird behaviors inside certain sections, I can stop using those certain sections. The nice part is that they will sort of always be lagging behind on this because they have to discover what the malware or the antivirus software is triggering on. So they're going to be a little bit behind the curve and trying to update the malware to keep up with the newest heuristic scanning. Other problems with neural networks, you can kind of overtrain one. So you can either feed it so many samples that it starts to generalize to the point where it thinks everything looks like malware. Or the opposite can be true. You've given it so many specific samples that what it's looking for is too narrow a set of details to really match a broad spectrum of malware. So to overcome this notion of overtraining or being too specific, what you can do, or what some researchers have done, is actually train up sort of a team of neural networks. So each member of this team has maybe been trained to identify certain behaviors. So you feed the sample to every member of that team and they all come back with like a vote. Right? Then you can use something like a voting or a consensus algorithm to look at everyone's vote and sort of put it together and decide what course of action you're going to take. It's kind of similar if you've ever seen, there's like an anime from like the 90s that was called Neon Genesis Evangelion, where this military group had these 3 supercomputers, and they would all analyze a scenario, and they would all sort of vote on what they thought the scenario was. In a way, we can use neural networks to do the same thing, right? We can all analyze a malware sample, and we put all of our votes together, and if we have enough votes to pass whatever we decide that pass threshold is going to be, then we flag the sample as being malicious. So we're going to talk about a few other things outside of detection. One of them is disinfection. One thing that people might want to do when they get a piece of malware is to try to clean the machine or clean the infected executable. If you can at all avoid it, don't. Just don't. It can be really difficult. It's error prone. It's a potentially risky operation because once you start deleting files, deleting registry keys, or even patching a binary, you run the risk of losing data, of corrupting a system, of introducing instabilities and unknown activities. You also run the risk of just missing some of what the malware left behind. So it's difficult. You do it on these situations where you absolutely have to, but if you can get away with doing like a reformat, then that's better. Just do that. Again, yeah, typically the best approach and the most cost effective too for any organization is going to be like flash the hard drive, put on your standard corporate image, and just go back to work. However, even in those instances, it's probably a good idea to still take a forensic image of the drive or whatever it is, because you still want to do some analysis on your own and see what happened. Some other problems that can crop up if we have automated disinfection, there's the risk of false positives, right? So there have been instances where an AV suite has used maybe a poor hashing algorithm and it's identified a legitimate system file as being malicious, and since it had automated disinfection turned on, it just deleted a legit file on a file system. So there's some danger there. Also, automated disinfecting versus like malware families. So since not every malware variant inside of a family is the exact same, they may require different removal processes, right? Maybe some of them put files in one location, some put files in another location. So again, you run the risk of either destroying real and legitimate files, or you could miss some of the files that a particular variant left behind. So again, we have a bit of a risk there. So we're going to move on from that to like what you would look for if you actually do want to write some disinfection routines. So one of the things you can do is monitor the file system, right? This is where you would turn on all your sysmon, your regmon, all of your network traffic analysis, all of your process monitoring stuff, and find out what the sample is doing. So if it's making changes to the file system, again, whether that be to the registry, it's creating files, it's editing files, you want to record that and essentially reverse those operations that it's making, right? So you can come up with a list or a sequence of steps that someone would have to go through to delete the malicious registry keys, for example. Other things you can do is observe the creation of any secondary watchdog processes or any backup routines, any scheduled tasks, anything like that that could regenerate the malware, or any backup files that the malware's made, and then go and delete those files and make sure that you've deleted every last copy of them. Also that they're not resident in memory, so you can go and terminate all those running processes. In the case where you actually have an infected executable and you're trying to clean it, again, like this is crazy, you should never have to do it, but let's just say you end up in a strange circumstance where it is absolutely critical that you disinfect this executable because it's mission critical for some reason. I don't know. You can imagine a reason why that might be. What you can do is sort of debug or trace or step through the program to identify just the malicious behavior, and you can try overwriting that malicious code with no op instructions, or if you find like the branch in the code, like the else statement that takes you into the malicious code, if you just comment out that else or that condition, then you'll never branch into that code, and you can essentially lock off that area of the program if you needed to for some sort of short-term reason. Again, we generally wouldn't do this, but if you had to, that's how you would do it. In addition, we also, as part of disinfection, need to figure out how this infection happened in the first case, right? Was it because an attachment came in over email? If so, it's not sufficient to just delete the attachment. You should also delete the initial email that contained the malicious attachment, right? We want to prevent the infection from happening a second time. Inoculation is an interesting concept. So a lot of times malware authors will introduce the concept of a marker or a flag that they will put either on a file or on a system that they've infected, either because they don't want to infect it again or because maybe they don't want to infect their own systems. So they will put this marker on their own systems they don't get themselves. One example might be here. We have a ransomware strain that, it doesn't want to waste CPU cycles by continually iterating over a directory, re-encrypting the same files over and over and over again. So maybe it writes into the files it's already infected a new modified timestamp, and maybe it sets it to February 3rd of 1970 or something like that. So every time it's about to encrypt a new file, it checks the modified timestamp. If it sees this specific value, it knows, oh, I've already encrypted that, and it can move on to the next file. So what inoculation means is that we could then, knowing this flag or this value gets set, we could apply that to every file in our file system, right? So that way, if you got this ransomware strain, it would observe all the files, it would see this and think that it's already encrypted the files, even though it really hadn't. So in a way, we're sort of preventing the infection, or we're preventing the spread of the infection with this inoculation. However, they can be error prone. So if we imagine a scenario like this, where, I have two strains of ransomware. Ransomware A sets the modified time to, February 3rd, and ransomware strain B sets the same timestamp, like the same modified timestamp, to January 1st of 1971. Since a file can't have two different modification timestamps or two, different inoculation values because they conflict with each other, then we would have to pick one of the two. Also, it's just inconvenient to have to do things like, proactively change timestamps on our files because they make, the system perform less reliably, right? We can't do certain types of date filtering on files, which you might want to do. It's just normal system operations. So we don't tend to use inoculation very much, but where you might want to look at it as a technique is a situation where maybe, there's a worm that's spreading really quickly and there's no patch right now, but you did hear that, there's a particular flag or inoculation value that you can set. So you might do that really temporarily just to stop the spread. If you're aware that's something that's out there until a patch or, a proper malware signature can be identified. So that's where you might consider something like that. There are other techniques that we can use to fight malware beyond just malware scanning. So we've got, use of actual strict access control measures. So applying correct permissions to users, to file systems, to different resources, right? So that the malware is limited in what resources it has access to and to how it can move around a system. So, for example, you might want to move from something like a discretionary access control system to a mandatory access control system. Discretionary access control is, the stuff we're used to seeing in like Linux, where the creator and owner of a file can determine the permissions that file has, right? If I make a file, I can assign it like 777 permissions, right? I can give everybody read, write, and execute to that file. Where a mandatory access control system follows some kind of a preset policy that's set by an administrator. So even when a user creates their own file, they're not able to assign or manage permissions on it. And we can extend this beyond just a file and a folder to sort of any resource, like a network resource, or even an entire system. So locking down access control is one mechanism that can help prevent the spread or the initial infection by malware. We can limit functionality by applying and being diligent about our use of the principle of least privilege, right? So assign resources only the permissions they need to do their job. Again, we're limiting the availability and the things that malware can do to spread itself or to make impacts with its payload. We can limit the sharing of data and files to only sort of required operations. So only things that need to access the database are permitted to access the database. We can also implement, like row level access control so that if something does get in and starts encrypting our database, maybe it can't encrypt all the rows in the database. We also might consider like limiting transitive trust within systems. So in a scenario where like system A trusts system B and system B trusts system C, in the real world, sometimes we would allow the transitive property where system A could trust system C, but maybe in a computing environment, we don't always want to do that. That way, if system C is infected with malware, maybe it can backtrack and infect system B, but it can't directly go and infect system A if they don't necessarily share some sort of transitive trust relationship. So that's another consideration. We also have sandboxing in all its various incarnations. So, we have like browser tab isolation, so where every tab is like its own process, so it benefits from process isolation. We can use things like virtual machines or containers or chroot jails to isolate certain components, certain resources, so that if they are compromised by a piece of malware, they can't spread out of that sandbox or out of that container to infect the rest of the system. There's integrity checking, which has existed for quite a while and can be a fairly effective technique. So you would maybe hash all of the files in a file system or a subset of the files, and you store those hashes in a database. And then you regularly rehash all your files and you check them against the hashes stored in that database. If the hashes differ, if the hashes that I just took differ from the hashes in the database, then I know that the file's changed. Obviously, there's some disadvantages to that. Like there's a lot of files in a machine that change regularly, like log files and user files. But we can still apply this to certain system files, to DLLs, to certain libraries that really don't change very often. And those would be the kinds of things that malware would really want to go after anyways. So it's effective in that regard. There could be false positives if we get like weird collisions and things like that. It also, if we think about it, that first batch of hashes we take requires that our system be initially in a clean and uninfected state, which really we can never guarantee 100% if you want to get really picky. Odds are, a fresh install is probably okay, but there is the off chance that maybe your installer has been infected or something like that, or your gold image that your organization uses has maybe been infected, so even your initial database is a little bit corrupted. It also is kind of slow, right? If you could test this yourself. If you run like a little for loop that runs SHA-256 on every file in your file system, it's going to take a while. And if you're doing that regularly, if you're doing that on a gigantic server with tons of files, it's going to take a long time to calculate those hashes. For an example of a piece of software that has been around for absolute ages that does this and does this really well, the company Tripwire, who now offers a lot of different services, product solutions, whatever, started out as a simplistic file integrity program, and they still maintain an open source version of their software that you can use for not only file integrity checking, but it's got robust alerting it can do. Think of it as like an intrusion detection system, but for your file system. That's essentially what it is. We can also implement at the OS level like behavior blocking, right? So we can block operations, we can block libraries, we can block system calls that we know malware might want to use if our system never requires them. In something like an embedded environment where you have a lot of understanding about everything that should happen in a system. So if you think of your IoT devices, right? Maybe I have like an IoT light bulb or something like that. And the only things that it should be able to do are change colors and receive color instructions from some app, right? If it's running some like really primitive embedded Linux, I would strip out all the libraries that are not related to receiving Wi-Fi instructions and changing colors. Because if those behaviors aren't there, then malware that infects the light bulb and maybe as part of a botnet can't leverage or do anything else. All right, so by blocking things like that, we're making it more robust and we're proactively blocking that behavior. You can also remove software from systems you don't need. A common thing that's recommended is you don't have compilers on production systems so that malware can't recompile itself or recompile new exploits to compromise that system. You can also implement sort of dynamic behavior blocks or sort of real-time behavior blocking. So a number of years ago, one of the capstone groups in the ISS program was looking at ransomware. And one of the things they saw was that one of ransomware's steps is it usually deletes the volume shadow copy as one of the first things it does. So, you can monitor for that event and, trigger a behavior block or a process termination when you see that happen. So in that effect, you're also stopping the malware sort of early on. Another interesting approach to behavior blocking gets used in the OpenBSD operating system. So OpenBSD implements this interesting pledge concept where a system function or a system program says at the start of the program, I pledge to only use this subset of system calls, right? Maybe it needs open, it needs write, it needs exit, and maybe it needs connect. I don't know, maybe it just needs those calls or those library functions. And if the program calls anything outside of those functions, the operating system will terminate it because that means that the program has likely been compromised. Either it's been like buffer overflowed or it's been infected somehow. So the idea is that the pledge basically says this program will only run these system calls. If it runs anything else, then I've been compromised, so terminate that process, which is a neat take on behavior blocking. Anyways, that's it. That wraps up this last component of anti-malware activity, anti-malware solutions and options. So check Slate. There's going to be more exercises up, and we will resume with some dynamic analysis for the remainder of the classes. Okay, thanks.